Okay, so we're going to look at an old question, which is using a tangent line to approximate the value of a function. And then the second part is a new question that we can now answer. So let's start with the first part. Find the equation of the tangent line to this curve f at x equals 0. So the curve is 2x e to the x plus 1/2 at x equals 0. So let's get the ordered pair first. So what is f of 0? F of 0 is going to be 0 plus 1/2. That's my ordered pair. And now I need a slope. So I need a first derivative to get a slope. And the first derivative is going to be the product rule. So v u prime, so it's going to be 2e to the x plus u v primed, which is going to be 2x e to the x. The constant gets wiped out. And now I need a slope at 0. The slope at 0 is going to be, this part becomes 0, this is going to be 2e to 0, which is 1, 2 times 1 is 2. So I have a slope and an ordered pair, so the tangent line is going to be 1/2 plus 2 times x. So I can now use the tangent line to approximate values of the function nearby the point of tangency. So f of 0.125 is approximately equal to 1/2 plus 2 times 0.0125 is actually an eighth as a decimal, and so we're going to get 1/2 plus 1/4, which is 3/4. Okay, old news there. Now the second question is where we can now use some new information to answer. It says, is this approximation an over or an under approximation? So is 3/4 bigger than or less than the real y value at 0.125? How the heck are we going to answer that question? Okay, well, let's take a look at the picture. All right, this is what we would see if we graphed the function f in red and its tangent line in blue. Tangent line is taken at x equals 0, and we wanted to find the approximation for f of 1/8, which is roughly, I don't know, about here. And we use the tangent line's y value to do it. Now, with the picture, it's very clear to see that the tangent line would be an under approximation. The y value in the blue line is less than the y value in the red curve. Okay, so we can answer that question if I have the graph. But how would I know that without looking at the graph? Well, we just learned that we can tell where the tangent line lies on a curve based on its concavity. So the concavity can be examined using either the first or the second derivative. Let me shrink this stuff down and we'll take a look. Okay, so since I don't have a graph of the first derivative, let's find the second derivative and analyze its sign to determine the concavity of our function f. So our second derivative will be 2e to the x is its own derivative, and then we're going to do the product rule again, but we already know the answer because 2x e to the x was our original function. So we'll get another 2e to the x plus a 2x e to the x, and that can be simplified a bit to 4e to the x plus 2x e to the x. Alright, we'll set that equal to 0. It's never undefined. It's good for all real numbers. And then we'll make a sign chart for f double prime to determine concavity. Alright, so we need to probably factor out some common factors to make that a little bit easier to solve. So let's take out a 2 and a e to the x, which are common to both terms. That leaves us with a 2, and it also leaves us with a x e, sorry, the x e to the x has been factored out. All we're left with inside there is an x. Now, the first portion here, this is never equal to 0. Okay, 2 is positive, and the exponential function is always positive. So you're only looking at when is this equal to 0, and that occurs when x is -2. We do a sign test, and we're going to get negatives before -2, positives after -2. So what do we know now? We took a tangent line approximation at x equals 0, okay, and we used that to approximate values of the function when x was 0.125 or 1/8. Okay, so 0 and 1/8 are on the interval where f primed or f double primed was positive, so that's where f is concave up. So now we know that we used a tangent line approximation where our function was concave up, and when that happens, we will always get a tangent line that lies below the curve and therefore under approximate values. We have to be careful to mention intervals of concavity when we talk about whether a tangent line is an over or an under approximation to a function's value. Here's an illustration of why it's important. This tangent line is drawn at x equals -1/2, and you can see there are certain locations where the tangent line over approximates the value of the function, but there are also points where the tangent line would under approximate the value of the function. Okay, and that has to do with where this curve is concave down versus concave up. So let me show you a quick analysis so that you understand what you need to say, how you can say it, and what you're allowed to do. So this is the curve x cubed plus 1. The first derivative is 3x squared, and the second derivative is 6x. So to analyze the concavity, I'm going to look at the sign of the second derivative. So this is a sign chart for f double prime. 0 is a number that makes the second derivative 0, and I'll get negative values before and positive values after 0. So this tells me that f is concave down before 0, concave up after 0. Okay? Now, this tangent line at -1/2 will over approximate f on intervals where f is concave down. Okay, so as long as I stay on the interval -infinity to 0, okay, I'm guaranteed that the tangent line will over approximate the curve's values or the function's values. Once I get past this 0, though, I can't guarantee that anymore because the function is now concave up, which means that at some point this tangent line is going to be no good. So when we say I'm using concavity to justify whether a tangent line is over or under approximating the value of a function, I need to also mention where is the function concave down or concave up. Now, one other thing that's useful with the second derivative is to determine locations of local maxima or minima. Now, if you're told that the function's derivative at 2 is 0, that will tell you only one thing. Okay? At 2, there is a horizontal tangent on the graph of f. That's all we know. The graph is flat. So that could be one of 3 different pictures to us. The first picture would be a local minimum. The second picture would be a local maximum. And the last picture is a saddle point. Okay, but in each case, at 2, you have a horizontal tangent line. Generally speaking, to determine which of the 3 scenarios this is you make a sign chart for the first derivative and you test and see what happens. Okay, there are times where we can't make a sign chart, and that's where this next piece of information is helpful. Okay, so at this point, if I have no other information, I'm kind of stuck. All I know is there's a horizontal tangent at x equals 2. But if you add one more piece of information to me, okay, if you tell me that the second derivative is negative, I can pick which one of these 3 scenarios is happening. Okay, second derivative being negative, remember, means that f primed would be decreasing at 2, right? Which means that f would be concave down at x equals 2. So only one of these pictures will f be concave down at x equals 2, and it's the middle picture right here, okay, because the tangent line lies above the curve, down like a frown. So here's the test stated formally. It's called the second derivative test for local extrema. We already had a first derivative test, which says you analyze the signs on either side of your critical points. But now this says, okay, if your derivative is 0 at a spot and your second derivative is positive, then you have to have a local min. If your second derivative is negative and your first derivative is 0, you'll have a local max. And if they're both 0, we can't make any conclusions. Okay, that's still up in the air. So here's an example where you could use this second derivative test. There are some times where you have to use the second derivative test because the sign chart's impossible to do. So this is not a function as presented. You could solve it for y and get two different pieces and analyze them separately. But this will be easier if we do it this way. So they're asking us what happens at 0, negative 1. So let's take a derivative implicitly. So 2x plus 2y times y primed equals 0. We subtract 2x, we divide by 2y, and we get negative x over y is the first derivative. Okay. We notice that when x is 0 and when y is negative 1, so at this point 0, negative 1, y primed is equal to 0. So what does that mean? It means we have a horizontal tangent line, right? That's all we know. I can't do a sign chart. Okay, I can't do a sign chart for this because I have two variables to worry about. Now, I have a new test that says, hey, take the second derivative. So second derivative of a quotient, so I need the quotient rule. Leave that negative out in front. We get y times 1 minus x times y primed. Okay, but we know what y primed is. Y primed is 2 lines up. Y primed is negative x over y. So I'll replace replace y primed with negative x over y. Let's clean this up a little bit. This is going to be what? X squared over y, and becomes positive. So I have opposites of y plus x squared over y. And I'm sorry, that should have been a y squared to begin with because it's the quotient rule. There we go. Okay, so now I have a second derivative. And I need to analyze, okay, what's the sign of the second derivative at this point 0, negative 1 from our second derivative. Okay, we have a negative times a negative plus, when we plug in 0 for x, that vanishes, and the denominator is not 0, so that's good. The denominator is always going to be positive, so this is going to give us a 1 over 1, and 1 is more than 0. So what does this mean? If the second derivative is positive, then we are concave up. So if I have a horizontal tangent line and concave up, this has to be a local maximum. And if you know anything about this curve, x squared plus y squared equals 1, it's the unit circle. And at 0, negative 1, you know that the unit circle would have a local minimum. Please excuse the artwork.